Okay, so welcome everyone to this week's QTFMS talk. Today we have the pleasure of hosting Sahand Seifnashri from Princeton Institute of Advanced Studies, and he's going to talk about his recent work on symmetry transmutation. So, Sahand, thanks a lot for accepting our invitation. It's great to have you here today. You can take it away.
Hello, everyone. Thank you for the invitation. It's a pleasure to talk here. Okay, so today I'm gonna talk about this work that we put a couple of months ago. It's a collaboration with Nadi Seiberg about symmetry transmutation. And of course, feel free to ask questions and unmute and interrupt me in any time. So I don't, even if there have no time, it's not important to go to all the slides. So just it's better to make it more interactive. So just feel free to ask.
Just to clarify, we don't have actually a time limit, so you can go as long as if you are
Sure.
free after. So we don't have any time limits.
Okay, thanks. Right. Okay, so let me first start with an introduction. So, an interesting thing is that symmetries are very useful for understanding infrared phases of matters or some quantum field theories or some quantum many-body systems, both in the continuum or on the lattice. For example, they are useful for characterizing and classifying phases. This could be, as I said, phases of matter or some gauge theories, and also as some non-perturbative tools to analyze some strongly coupled theories that you cannot do perturbation theory for them. Okay, and an example of these are just, first of all, the first one is the classical Landau paradigm, that we know that we can organize phases of matter by local order parameters for spontaneous symmetry breaking, order disordered phases that we know, like liquid, gas, so on. And the second one is using 't Hooft anomaly, the celebrated 't Hooft anomaly matching, to constrain dynamics. And if you have some global symmetry, it has a 't Hooft anomaly. Okay. But there exist many phases that are beyond Landau paradigm and many strongly coupled gauge theories that are not constrained enough by just ordinary symmetries. And it turns out that sometimes there are some generalized symmetries, and you could use these generalized symmetries to provide a unified framework to characterize many, many known gapped phases of matter. So if you just also include these generalized symmetries and constraint some strongly coupled non-abelian gauge theories that you cannot constrain using just ordinary symmetries. So generalized symmetries are as useful as ordinary symmetries. If you care about ordinary symmetries, if you think they are useful, and you should also care about general symmetries because they're as powerful as usual symmetries. For example, an example of this phenomena is what people nowadays call generalized Landau paradigm, which allows you to characterize phases through patterns of spontaneous symmetry breaking of generalized symmetries. For example, we know that usual ordered phases correspond to conventional symmetry breaking, like magnets. But there is this notion of symmetry protected topological phases, or SPTs for short, that you could understand them as spontaneous symmetry breaking of some kind of dual symmetries. So here you have some SPT phases, you have to gauge that symmetry, and then you get a dual symmetry, and then different pattern of symmetry breaking for the dual symmetry characterize SPT phases. So even SPT phases are in this framework of, symmetry breaking. And then we have topological order, which correspond to anyons. Like in QFT, they correspond to, we describe them by Chern-Simons theory, but there are some topological order and anyons, and they correspond to spontaneous symmetry breaking of higher form symmetries that I will review in this talk. I guess you had talked before about higher form symmetry in this seminar series, but I will review them again. And for example, in particular, we have confinement and deconfinement in gauge theories. And we could also distinguish these two from spontaneous symmetry breaking of one-form symmetries, as I will review. Okay, so this was just some introduction. And now, so the outline would be first I will review generalized symmetries, high-form symmetries in particular, discuss confinement, deconfinement a bit, and discuss one application, and then go to the main topic of the talk, which is symmetry transmutation. Okay. Any question about the plan outline? Okay. So let me start the review. So to understand generalized symmetries, let me just give a slightly different perspective on ordinary symmetries. So we know that there is a famous Noether theorem that tells us that if you have a continuous symmetries, they always lead to some conserved charges and conserved current, right? So if you have a continuous, let's say U1 symmetry, the statement that there is a J mu, there is a current, which is conserved. So d mu J mu is 0. And then you could write the charge by integrating J0 over all the space. So D is a space-time dimension, and here sigma is a spatial slice. Okay, I'm integrating J0 to construct a charge. And using the charge, you could construct a unitary operator by taking e to the I alpha q. And then, because this is conserved, you will conclude that this charge is conserved in time. It means that this unitary operator commutes with the Hamiltonian, right? But now the idea is that not only you have a charge which is supported on a spatial slice sigma, you could actually define a charge for any closed codimension one submanifold sigma inside the spacetime. Okay, so we have a d-dimensional spacetime. So the idea is to just take this conserved current J mu and construct this gadget out of it. And then the fact that J mu is closed, that is conserved, it means that this kind of differential form is closed by taking exterior derivative. So then, because it's closed, it allows you to integrate J over any closed codimension one submanifold sigma inside the spacetime. So you could also define these operators, these unitary operators or defects, for any closed codimension one manifold. And then we call that this U of alpha is a topological operator or defect. So what does it mean to be topological? The fact that it's topological, it means that this operator, it really doesn't depend on the details of sigma. It only depends on the topology of sigma. So if you take this sigma, it could be a sphere, for example, inside three space-time dimension. For example, if the space-time is 3-dimensional, it could be a 2-sphere. And then if you deform this 2-sphere a little bit, this expression doesn't change. Because if you deform sigma a little bit, perturb it a little bit, and you take the difference would be the integration over J over a ball, but then you could use Stokes' theorem to say that this is the same as integration of dj inside the ball, but since dj is 0, you conclude that the two terms are the same. So because dj is a closed form, it means that this operator is topological. So the value of this would only change if there is an operator insertion. But if there is no operator insertion, you could just change sigma and deform it at will. So it only depends on the topology of sigma. That's why it's called U alpha is topological. Okay. And so then the benefit is that you could use this fact to define the symmetry through this property. So you could define a symmetry by this topological operator defect. Okay, so this led to this notion of the modern definition of global symmetry as topological operators or defects. So, if you have a time direction, if you have some operator which is supported on spatial slides like this, is usually called an operator. But if some operator, it's stretched through time, it's called a defect. So in this talk, because we are considering Lorentz invariant or relativistic theories, there is really no distinction between operators and defects. So I will change this term. I will use this term interchangeably. Okay, so then you could define the symmetry as topological operators. And so what does it mean to define a symmetry by that? So it means the following. So you could consider the correlation function of your quantum field theory, and you could insert this operator U inside the correlation function. Then it means that the value of correlation function is really insensitive if you perturb it slightly, unless you cross an operator insertion, like O of X. This is a local operator. So if you cross the local operator, this U acts by the symmetry transformation on them. So here O prime is the symmetry transformation of O under this symmetry. So that is how it's constrained the local operators. So you define it, the symmetry through topological operators, and is given by that. Okay, so it turns out that using this definition, everything that you know about symmetries can be stated in this language of topological operators. For example, inserting a symmetry defect inside the spacetime corresponds to turn on background gauge field for this symmetry. So if you insert the operator on submanifold sigma, is the same as setting the background gauge field to be kind of a delta function on this sigma that is only non-zero on sigma, roughly speaking. Okay. And then symmetry action correspond to, so this picture for simplicity is in 1+1 dimension. So the symmetry operator is a line, but in higher dimension would be codimension 1. So, and to act on a local operator, you just wrap a local operator, uh, you wrap the symmetry operator around the local operator, and since topological, you could shrink it. And the answer doesn't change. And once you shrink it, you get a new operator that you call it O prime. So that's how you transform O to O prime. And using the other picture is the same as doing U O U inverse. Because this is topological, this is the same as inserting a line here and a line above and an operator here. So line above is U, line below is with the other orientation is U inverse. So using the topological property, this is equal to the same, and this is the symmetry action. Okay, so this is how you act on it. Any question so far? Okay, so now this leads to the notion of generalized symmetries. Led to this notion. For example, first we have the notion of higher form symmetries. So higher form symmetries correspond to symmetries that act on higher dimensional object. So in usual symmetries act on local operator that we write in a Lagrangian, but you could also imagine symmetries that act on line operators or surface operators. So for example, a one-form symmetry would be something that acts on a one-dimensional object, which is a line operator. So to define a Q-form symmetry, acts a codimension Q+1 topological operator, which acts on Q-dimensional object. So in this picture, I'm taking the case of, let's say space-time is 2+1, space-time is 3-dimension, and then you have a one-form symmetry. So the topological operator is codimension 2. So this red line is your symmetry operator, is topological, and this L is a non-topological operator, is some Wilson line or a 2 line that I'm acting on it. And the action is by you wrap the line on L and you get an symmetry action. So often L prime is L times to a phase. So it's better to put it would have been better if I had to put a phase here, which would be the action of U on L. And so then these also form a group usually. So there are some invertible symmetry, and the group structure is given by fusing these two line operators. So you put two of these close to each other and they obey a group multiplication law. There's also a notion of non-invertible symmetries, but for this talk it wouldn't be relevant. It's just the same thing, but you don't require that these topological operators have inverses. So now let me go to an example. So what's the easiest example of these higher form symmetries or generalized symmetries? It turns out that the simplest example is actually the example that we learn in undergrad in electromagnetism, right? So, when we learn Noether's theorem, it often taught that we have the conservation of electric charge and magnetic charge. But the electric charge and magnetic charge that you go and measure in undergrad lab, they are not actually zero form symmetries. They correspond to one form symmetries. Because in lab, once you are measuring the electric or magnetic charges, you're using Gauss law to measure them. So you have some macroscopic object and you are measuring its electric charge. So this macroscopic object that you are measuring its charge is not a local operator. It's actually, if you look at it in space-time, it's a line operator. Because there is a macroscopic object is sitting here. It carries an electric charge, but it's just a heavy object which is sitting there. So inside the space-time, it has some trajectory. It's some heavy particle. It's a line operator, and you're actually measuring the charge of this line operator through Gauss's law. So because the usual electric charge is kind of gauged, so it's a gauge symmetry, and you cannot measure the charge of a gauge symmetry. So the usual electric and magnetic charges are actually one-form symmetries that we measure in lab. But somehow, ironically, we first learn about zero-form symmetry and then one-form symmetry. So now let's describe it more mathematically. So we have, let's look at just the Lagrangian in 4 dimension. We have just F mu nu, F mu nu. We have this Lagrangian. A is a gauge field, dynamical gauge field, and F is a curvature. So it's for the U1 gauge theory. And it has U1 electric one-form symmetries and U1 magnetic one-form symmetries. So there is also some Noether current for these, but these are two forms. So the Noether current for the magnetic symmetry is F itself, and the Noether current for electric charge is star F. So these are conserved charges because if you take the exterior derivative, dF equals 0. dF equals 0 by Bianchi identity, and d star F equals 0 by equations of motion. And so because this is 0, so then this operator would be topological. If you integrate F over a closed surface, this is topological. This is just the usual Gauss law, and this is the electric version of it. Because of kind of so-called Gauss law, we know that the charge inside the sphere, it doesn't depend on the shape of sphere. You just measure the total charge. That's basically it. And then if you have a Wilson line in space-time, you could wrap this surface around it. So I'm just ignoring the other direction. And then once you wrap around it, you measure the charge. So alpha would be the charge of this. So here the Wilson line has charge 1, so I just get e to the I alpha. But if this Wilson line had charge n, I would have gotten e to the I alpha n. So I could measure the charge of the Wilson line. And also the same if you have a toothed line, which carries a magnetic charge, you could measure its magnetic charge through this. Okay. Any question?
Sir, I
Right.
have a question. Can you
Yes.
show the previous slide, please?
This one?
Yeah. In this example, you talk about higher force symmetries, right? As an example.
Yes.
In the second one, the non-invertible symmetries, I can see that there is a, how can I say, fusion algebra. And when we consider the Ising models,
Mhm.
any form of it, and consider unique excitations, and they obey this kind of relations. So, is this unique excitations obey non-invertible symmetries, or anions are just come and pop from non-invertible symmetry operations? Is it true?
Yes, true. So first of all, in this talk, I'm not going to talk about non-invertible symmetry. I just wanted to mention it. But to answer this question is yes. So in the low, so the phenomena is that if you go to the low energy theory, then the anions, so anions are some quasi-particles, they have some mass. But if you go below their mass, if you go to energies below their mass, all it remains from them is just these topological line operators for the anions. And yeah, so it's true that anions form these non-invertible fusion rules, and in the low energy theory, you could think of the word line as some topological line operator that generates some non-invertible one-form symmetries. So that would be an
Okay.
example.
So, is it an emergent symmetry? Although
That's
it's
right. It's an
non-invertible.
emergent symmetry because you
Okay.
have to go below their mass. Sometimes it wouldn't be an emergent symmetry. And this talk actually would be exactly the topic of this talk would be to distinguish between what kind of one-form symmetries are emergent and what kind of them are not emergent and they already exist in the UV. But I will talk about just ordinary invertible one-form symmetry because you could also have abelian anion, and the abelian anion generates an an invertible one-form symmetry. So I will not talk about this case, but I will talk about emergent or ordinary invertible symmetries.
Okay. Thank you.
Yeah, thanks for the question. Any other question? Right. Okay, so now let's also discuss the SUN gauge theory. How about SUN gauge theory? Is there one-form symmetry in the SUN gauge theory? Like in the ordinary U1 gauge theory, we have electromagnetic charges. Do we have electric SUN charges or magnetic SUN charges? So it turns out that the situation there is more complicated, primarily because dynamical gluons, they self are charged, unless the photon. Photon doesn't carry any, it doesn't have any electric or magnetic charges. But gluons have charges and they can partially screen the charge. So you cannot measure these SUN charges in general. So more precisely, gluons transform under the adjoint representation of SUN. So if you have a Wilson line and you want to measure its charge, so the charge of a Wilson line is basically its representation under SUN, right? For U1, representation of U1 is an integer, that's the electric charge. But for SUN, its charge is a representation of SUN. But because of gluon, you could only measure this representation modulo the adjoint representation. And the fact is that SUN representation transforms trivially under the center, Zn center of SUN. So it turns out that modular adjoint representation is the same as measuring only the Zn charge. So basically you only have a Zn one-form symmetry. Out of this big continuous symmetry, there is only a discrete symmetry. And so there is a Zn one-form symmetry, that electric one-form symmetry that is generated by some kind of topological surface operator. I call it U of E. And was there a question? Oh,
I'm sorry.
no worries. I admit that. Okay, so there is a surface operator, and if you wrap it around the Wilson line, you could measure this representation. So you cannot completely determine the representation R. You could only measure this charge Q of R mod n. So what is Q of R mod n? So in the representation R, there's a Young tableau representation, and you would count the number of Young tableau. So the number of Young tableau mod n is this charge. So there is a way to count this number mod n. That's all you have. It's just a Zn one-form symmetry. And you have this Zn one-form symmetry in any SUN gauge theory, given that all the matter fields transform trivially under this center of the Zn. For example, in adjoint QCD or something like that, you have always this Zn one-form symmetries. So now, using this language, you could also talk about confinement and deconfinement and rephrase the criterion for confinement and deconfinement in this language. For example, we know that confinement is defined by an area law for a large rectangular Wilson loops, because a large rectangular Wilson loops inside the expectation value just tells you, so what does it describe? It describes the creating proparticles separating for some distance, and then there is some potential energy between them, and let them evolve. So if there is a confining potential between them, and the area law measure this, you get an area law if there's a confining potential, because this potential is linear between them. So it's a linear charge times time. So confinement corresponds to area law. So this is a linear potential, and area law means that this kind of becomes zero for a large loop. And then deconfinement corresponds to a perimeter law. Okay, so now you could interpret the first one by saying that, so in particular the second one by saying that Zn one-form symmetry is spontaneously broken. Why? Because you could view this Wilson loop as an order parameter for your symmetry. So this Wilson loop is something which is charged under the Zn one-form symmetry, and yet its expectation value is non-zero. So it's the analog of a two-point function for local order parameter. If you have usual spontaneous symmetry breaking, you could measure it by a two-point function of two charges which are very far apart. And then if there's a unique vacuum by cluster decomposition, this should be the same as one-point function. And then, yeah, we will conclude that should be non-zero. But then for area law, this pool vanishes, and you don't find any order parameters, so then the Zn one-form symmetry is preserved. Okay, so using this language, confinement is Zn one-form symmetry is preserved, but deconfinement, it means Zn one-form symmetry is spontaneously broken. So in particular, you could think of the photon as the Nambu-Goldstone boson for spontaneous breaking of electromagnetic one-form symmetries. Because in that case, you have a Coulomb law, which is not a linear potential. So you are in this case that the expectation value is not vanish. Okay. Any question?
Can I ask something?
Yes, please.
So usually when discussing confinement, people say that if the potential is linearly proportional to something, that something is the string tension and the theory is confining. But can it be the case that the potential between two probe charges be like proportional to r squared or r cubed higher order r third. Like I never saw people discussing things like that in confinement. Why is it always the case that we only look for linear potentials?
Yeah, good. So it's not always actually linear. So the linear approximation is to just get a tension, which is physical.
Hmm.
But for example, I will discuss 2 plus 1D example. The simplest one simple example is just free U1 gauge theory in 2 plus 1D. And that's more subtle. So there you kind of get a log confinement. So the potential grows at a
Hmm.
log. So it's still kind of it's still confinement, but it's a very like a long time or long, yeah, it's a very slow confinement because it just only grows as a log. So you could in principle have different behaviors. I'm not sure if
Okay.
there is a bound and all of them could happen, but it's not that it's always like that. So it's just some rough.
Hmm. So the leading term coefficient has the physical interpretation of the string tension. Is
Yeah,
there
so
a
the
physical
linear one.
interpretation? Uh-huh. Is there a physical interpretation for the, like, let's say, R square coefficient, or they are not like physical parameters?
I mean, I think that there might be some dimension full parameter like a string tension, and the other there would be some other number that you could compute. Yeah, I think it'd be important to compute. That still would be.
I think Burak's question is whether there can be any term higher than linear.
Uh-huh.
Yeah, is that possible? That's his question.
Okay, for R
I
squared.
don't. Yeah, can it be R square? I don't think so.
Uh-huh. Uh-huh. Is okay. Is there a reason, particular reason that cannot happen? Good question. I don't know the answer.
Uh, for example, if you look to Polyakov model, the space is built with monopole instantons. If the flux were spread through the space, in the presence of monopole instanton, that would cost R square energy. So it would be proportional to the R square. However, the flux, whenever you have a flux tube, that directly implies that there is a linear potential. That's the flux emanating from quark does not spread through space. If it, as you said, if it was free empty space, it would cost log R. If it is a space filled up with monopoles, and if it still spreads uniformly, it would cost R square. But there is
Yeah.
then the confinement kicks in. It's energetically more favorable to form a flux tube and drop from R square to something linear in R.
Yeah, it would be always. Okay. Yeah, thanks. Right.
Thanks for
Sure.
the answers.
Right. Any other question? Okay. Okay, so now let's discuss just one application of this phenomenon, just which is one that there are of course many papers and many applications. I just use this famous application which is related to the topic of anomalies and higher form symmetries of this language. So for example, what's the famous question and the very difficult question is that what is the infrared phase of just pure Yang theory if we could solve it analytically, and it's a famous open problem. It's believed to be is one of the clay problems that the theory has a mass gap and it's confining. But how about the theory at theta equals pi? So you could add a f edge f, which is a topological term, with theta equals pi to the theory. So pure Yang at theta equals pi actually has a time reversal symmetry and also ZN1 from symmetry for any values of theta. So this paper, they discovered that there is actually a 't Hooft anomaly involving Z2 time reversal and ZN1 from symmetry. And so it means that there is an obstruction to gauging the ZN1 from symmetry while preserving the time reversal symmetry. And actually, it's gauging both of them. So you cannot gauge ZN1 from symmetry on orientable manifold. But the detail is not important. The fact that there is a 't Hooft anomaly implies that infrared theory must be non-trivial. So for theta equals 0, the infrared theory is conjectured to be trivially gapped. But just the fact that there is a 't Hooft anomaly, it tells you that the infrared must be non-trivial. And the interesting point is that this theory is strongly coupled. We cannot solve it analytically, but just by knowing the 't Hooft anomaly, we have a very powerful result about the non-triviality of this theory without needing to solve the theory analytically. So it's a very powerful result. So in particular, there are three different scenarios. So there are actually four scenarios, and in this paper, they rule out one of the scenarios. And so the three remaining scenarios is that the first scenario is that the theory is confined, and also the first scenario is time reversal is spontaneously broken. The second one is deconfinement, meaning that Z and one form symmetry is spontaneously broken. And the third scenario, the theory is gapless. So it's either gapless, but if it's gapped, it has to break one of the symmetries spontaneously for anomaly matching to work. So deconfinement is breaking of that. Time reversal broken is the first one, and this is then gapless. So, but it's believed that the first scenario is true. It's believed that the theory is confined and is gapped, and the time reversal is spontaneously broken. So you have two different vacua. This is the belief, and there are various still works on this, some lattice simulation or something, or numerical simulation to show that this is indeed the case. That was the application. Any question about this?
I have one question. So,
Yeah.
In the SUN gauge theory, if we restrict the instanton sectors to some proportion to some integer p, then that corresponds to gauging some ZP subgroup of the U1 instanton symmetry. And there is a ZP triform symmetry emerging, like quantum dual symmetry. And between the center symmetry and the triform symmetry, there is a mixed anomaly. And when you try to gauge this Zn, there is a four-group structure. So if we include this theta equals to pi, where there is this additional 't Hooft anomaly with the time reversal between center symmetry, and if we gauge the instanton symmetry so that there is another anomaly between the center symmetry and the triform symmetry, what kind of changes would we have in the possible phases of the theory?
Okay, so you want to first consider the sum over the instanton to be multiple of 3 or something. So you want to gauge.
Yeah, exactly.
And then, okay, first I have to remember that if this anomaly persists, okay, if it's multiple of 3, and this is kind of a mod 2 thing, it's kind of a Z2 phenomena. I think the mod 2 and the Z2 things, they still should be compatible with each other. So I suspect that this anomaly should still be there.
Okay, but like
if you're
if we
asking
get,
about the phases, I guess if you assume, so usually this kind of gauging or this manipulation commute with the RG flow. So if you conjecture that this phase, for example, is the first phase is confined and time reversal is spontaneously broken, then you should be able to do the gauging and see what happens to this theory.
I see.
So I think if you do that, you usually get different sectors. So you get different kind of a preform symmetry, as you said. So you get kind of 3 copies of the same system, something like that.
I see. 3
Yeah.
copies.
So depending on if you restrict it to be multiple of n, you usually get some kind of Zn preform symmetry, and you might get n copies of the same system. I'm not
Okay.
sure that's my guess, but yeah, I'm not sure if you get something interesting. I don't know. Yeah, it's a good question. I don't know. Something.
But when we restrict the instanton sum and gauge the center symmetry, there is a hybrid
Oh,
structure.
no, that's different from gauging the center symmetry. So if you consider this instanton sum to be multiple of n, that's more like a gauging a -1 form symmetry. Because this theta angle is like you could think of it as kind of a -1 form symmetry.
Yeah,
And
but I'm saying like gauging them both, like in sequence.
Right.
Like first gauge the instanton symmetry. You have some mixed anomaly between the triform symmetry and the center symmetry. Then you gauge the center symmetry.
Yeah, I haven't thought about it. Yeah, we'll discuss it later. Yeah, I cannot answer it.
Okay, thanks.
I have a comment.
Yes, please.
So in I know In the semi-classically calculable regimes, for example, on R3 cross S1, much before these works, actually, it has been shown that at theta equal pi, for example, monopole operator effects dies off because of the interference, and you do get, charge 2 monopoles, and you see that the time reversal symmetry is spontaneously broken. I think dynamically it's also very, very nice scenario. This anomaly constraint is also very nice, but we also have a clue in the sense of dynamics on what's going on.
Yeah, that's true. Thanks. Yeah. So it's not certainly the first paper. Yeah. That mentioned this phenomena. It's just the fact that it's just you could use it, you could show it very non-perturbatively and analytically exact. But yeah, indeed, there would be many clues before that. Yeah, thanks.
Thanks. Yeah. Thanks.
Midhat. All right. Okay. So now let's go through the main topic, the symmetry transmutation. So let me again motivate this phenomenon of symmetry transmutation that I'm going to discuss. So the goal of, one of the problems that we are interested is that we have some UV theory, like some non-abelian gauge theory, and we want to understand this infrared phase. Okay, so we have some UV theory, we do RG flow, we want to find the IR quantum field theory. And then we have, more importantly, we also have some symmetry in the UV that I denoted by GUV. And it has some tooth anomaly that I denoted by alpha UV. And then in the infrared, there is also some symmetry group GIR and some anomaly. Okay, so G is the global symmetry for me always, and alpha is tooth anomaly. And so one thing that we want to understand is there is exactly this arrow. What is the relation between GUV and its anomaly and GIR and its anomaly, right? So for example, anomaly matching, it's an example of understanding this phenomenon. So that's what we want to understand. The goal of the talk is to understand exactly this arrow. What's the relation between the symmetry in the UV and IR? They're not always the same. They could change. They could kind of transform or transmute to a different form or something. Okay. So let me just review the case, the ordinary case. Let's just stick with ordinary zero form symmetries and let's say internal symmetries. Just some discrete or some U1 or Zn symmetries. So what's the relation between GUV and GIR? So it turns out that the relation between GUV and GIR is some kind of homomorphism that people use in the literature. So there is some homomorphism that I denoted by phi between GUV and GIR. Basically, it means that if you have some symmetry transformation that acts on the UV, you can track it and it will also act in the infrared, but just it would be an element of the GIR. So it's a homomorphism. So importantly, this homomorphism may not be injective. It means that this might have a kernel. So kernel means what? It's some element that map to identity. So it means that there might exist some UV symmetries that do not act faithfully in the infrared. Okay. So for example, you could have some particle which carries some charge, but in the infrared, that particle is very heavy, so you don't see it. So that symmetry will act trivially on all the low energy degrees of freedom. So the degrees of freedom which are charged on it are heavy and they're not in the infrared. So it's injective if the symmetry does not act faithfully. Okay. And then it also might not act, the homomorphism might not also be surjective. It means that there is something in the GIR which is not in the image of phi. It's something in the co-kernel. And they correspond to the notion of emergent symmetries. So these are symmetries that just kind of emerge out of nothing. So they are not image of phi. Okay, so this homomorphism is not injective nor surjective. Any question? Okay, so now let me discuss more about this notion of exact versus emergent symmetry. So in general, there could be three types of symmetries in GIR. So the first one are emergent ones or approximate symmetries. Those are the ones that are in the co-kernel, they're not in the image. And then there are some symmetries which are not new symmetries, they're already in the UV, and they would be exact. So there are some symmetries which are present in the UV, and they also act faithfully in the IR. So if it's already in the UV and act faithfully in the IR, so it would be a symmetry in GIR, which is not new. It's an exact symmetry. But the third one is the most interesting one. These are symmetries which are new symmetries, meaning that they are not inside GUV, but yet they are exact. So I will discuss an example. So it's something in the image of phi, but is not in the GUV. So mathematically speaking, is some subgroup G in GIR, which is a non-trivial extension of the kernel and G. So there could be some Z2 subgroup in GIR, which is in the image, but is not in an image of a Z2. It might be an image of Z4 or something. Okay, so the topic of this talk will be this third type, which is new and exact. So let me discuss a very elementary example. This is very elementary. So a case from Z4 to Z2. So just consider a complex scalar field and a real scalar chi with this Lagrangian. Okay. So this Lagrangian has a Z4 symmetry. So phi has charge 1 mod 4. So if you send phi to I phi and chi to minus chi, this Lagrangian is invariant. Okay. So now imagine a scenario where the field phi, the complex field, is much heavier than the real scalar field. Okay. So now if you go to the infrared, you don't see the particle phi, you only see chi. So you integrate out phi and you only see chi, and the low energy Lagrangian has a Z2 symmetry, which is chi to minus chi, right? But this chi to minus chi is actually coming from this Z4 symmetry. So it's not an emergent symmetry, it's exact. As long as you preserve Z4, this Z2 will be preserved in the IR theory. But this Z2 symmetry is not in the UV, in the sense that there is no Z2 subgroup in the UV that implement this transformation. So Z2 is a quotient of Z4 instead of being a subgroup of Z4. So this chi to minus chi is a Z4 transformation in the UV. So there is no such a Z2 transformation in the UV. But since it's in the quotient of, is in the image of Z4, is exact. So this is a case of an exact symmetry, meaning that it cannot be violated by irrelevant term. So if you could add irrelevant term to the effective Lagrangian, but as long as you preserve Z4, this Z2 will be preserved. But the subtle fact is that there is no Z2 symmetry in the UV that implements that. It's only a Z4. Okay. Any question? So this phenomena is simple, but what I will discuss next would be something which is very similar to that. In that case, the UV symmetry would be an ordinary symmetry, but the infrared symmetry would be a one-form symmetry. So you could say that, yeah, you will see that this simple phenomena can become something interesting involving higher form symmetries. But this was just a warm-up for what do I mean by symmetry, which is exact, and also new. Any question? Okay, let me also discuss that you could also do anomaly matching if you have this homomorphism. And the statement of anomaly matching is that you could use map phi to map background gauge fields of UV and IR. So using this map, you could map background gauge field of UV to IR. So just using this map phi implies this capital phi under background gauge field. And the statement of anomaly matching is that, let's say alpha IR and alpha UV are the UV IR and UV anomaly. And anomaly matching tells you that this phi has to satisfy this equation. So if you use the UV anomaly and map it to the AIR and input it the alpha IR, you should get that one. So that's the statement of anomaly matching in this case. So let me not get to the anomaly matching too much. Let me just pass through it quickly. So let me just mention 2 points very quickly. So first is that anomalies of emergent symmetry do not match in the UV. So for anomaly matching, we don't consider emergent symmetry. Another subtle point is that exact symmetries can have emergent anomaly. But okay, it's not important for this. The rest. Okay, let me just go to the topic. So the goal of this talk, this part, would be to study the situation where an ordinary zero-form symmetry in the UV leads to an exact higher-form symmetry in the IR. So this is an exact as opposed to an emergent symmetry. So in particular, we would discuss this phenomenon of what we call symmetry transmutation, where the UV global symmetry does not act faithfully in the IR, like the Z4 example, but instead acts effectively as a higher form symmetry in the IR. Okay, so we said that GUV is transmuted into a higher form symmetry in the IR, and we mathematically describe it by a map between their background gauge field. And unless the usual case of groups of ordinary symmetry, this phi is not coming from some homomorphism. So we don't have any homomorphism between groups anymore. We just have a map between their background gauge fields. And such a map has been discussed before in many papers. I will discuss examples. Okay, so importantly, transmuted symmetries are exact rather than emergent. Okay, and the word, just want to mention that the word transmute is very appropriate, because if you look at its definition in the dictionary, it says that change or alter in form, appearance, or nature, especially to a higher form. This was in the dictionary, so it was just fits for our bill. Okay, good. So let me mention that symmetry transmutation is closely related to symmetry fractionalization, especially in 2+1 dimension. And the classical example of this is actually in fractional quantum Hall effect. So what happens in fractional quantum Hall effect is that the macroscopic or UV theory has a U1 global symmetry. So in nature, it's just the electromagnetic symmetry, which in the condensed matter system, you could think of it as a global U1 symmetry. And this macroscopic UV U1 symmetry is associated with charge conservation. It actually is transmuted into a one-form symmetry, which is generated by some kind of anion, which people usually call the Wison anion. And in equation, it tells you that dAUV, so AUV is a background gauge field for this U1 macroscopic symmetry. You could treat dAUV become some kind of a two-form, which is a two-form background field for this one-form emergent, or in this case, it would be an exact transmuted symmetry. So you could use this fact in the Lagrangian to probe this one-form symmetry that is generated by Wison. So fractional quantum Hall is the classical example of this symmetry transmutation from U1 to a one-form symmetry. But this could be more general than that. And that's what we want to discuss. So let me discuss some necessary conditions for this symmetry transmutation to happen before discussing an example. So mostly we're going to discuss a transmutation from zero-form symmetry into one-form symmetry. Okay, so let's say we have some zero-form symmetry by group G into a one-form symmetry by some abelian group K. So this will happen if at least these three conditions are satisfied. First, the zero condition is that we don't want K to be a symmetry of the UV. We want it to be a new symmetry. If it's already in the UV, it's not transmutation because it's not new. Then the other condition is that G0, the UV symmetry, should not act faithfully in the IR. Okay? And if it doesn't act faithfully, it could be that still some line operators, it acts projectively on some defects or line operators. If it acts projectively on line operators, then generically we have symmetry transmutation. So I want to mention that this is really common in gauge theories with massive matter fields that transform under a projective representation of the global symmetry group. So we'll see an example of it. And so whenever the matter fields, so these are not local operators because they are not gauge invariant. If the matter fields transform under a projective representation of a global symmetry, this symmetry transmutation generically happens. So symmetry transmutation then happens below the mass of these such matter fields. So you have some matter fields transformed under projective representation. You go below their masses, and you integrate them out, and you get transmutation, which can have some interesting implication for anomaly matching and so on. Okay, again, so let's
Can I add
consider
something?
Yes.
So since the G0 group acts projectively, can we say that the real symmetric group is the central extension of this?
That's right. So if you have a projective representation, then the matter field would transform linearly under a central extension of that. And this central extension actually would be important if you want to mathematically describe the pattern of symmetry transmutation. So the answer is yes, and there is some central extension which will be important, but I will not maybe discuss it that much, that central extension. In the paper, we discuss, yeah, the implication of it. Yeah.
Thanks.
Okay, so let's discuss just in 2 plus 1 dimension, in 3 dimension, QED in 3 dimension. So let's consider scalar QED with 2 flavor. Okay, so we have U1 gauge theory coupled to charge 1 scalars phi1 and phi2. Okay, this is Lagrangian. Have the kinetic term for the gauge field. And let's also consider some Chern-Simons term. And then there's a kinetic term for the matter fields and some mass term. Okay. So here, this theory has some SO3 global symmetry, which acts on gauge invariant operators. So this, but however, phi1 and phi2 transform projectively under SO3 because phi1 and phi2 transforms under a doublet. Okay, they're a doublet, so they're kind of a spin a half representation, but they are not gauge invariant. So the symmetry that acts faithfully on gauge invariant operator is actually SO3. Okay, so yeah, so then you have the SO3 symmetry. So phi1 and phi2 transform on the doublet of U2, where U2 is this group, but U1 subgroup of U2 is gauged. So the global symmetry is U2 mod U1, which is actually SO3 instead of SU2. Okay. So in this case, matter fields indeed transform under projective representation of the global symmetry SO3F. So what it means is that the Wilson line, which are the word lines of this matter field, transform projectively under SO3. Then it lead to the fact that at low energies below the mass of the scalar fields, the SO3 symmetry is transmuted into a Z2 one-form symmetry acting on the Wilson line. So the existence of the charge 1 scalar breaks the one-form symmetry of the Lagrangian. So you would think that in the low energy theory, below the mass of this matter fields, you have just pure QED, and it has a one-form symmetry, and you think it's emergent, usually. But in this case, it's better than being emergent. It's actually transmuted from the SO3 symmetry. So you could use the UV SO3 symmetry to probe this infrared one-form symmetry. You could turn on background gauge field for the SO3 to turn on background gauge field for this one-form symmetry in the infrared. So this one for Z2 one-form symmetry in the infrared is not emergent, it's exact. You could probe it, and you could use anomaly matching for that on less emergent symmetries. So there are actually 3 ways to see this symmetry transmutation. One way is by turning on background gauge field. So if you write the Lagrangian, you could see that if you turn on background gauge field for the SO3, it actually turns on the background gauge field for the one-form symmetry in the infrared. So, and the relation is a bit complicated in this case. So B is a Z2 two-form discrete gauge field. It becomes the second Stiefel-Friedling class of this gauge bundle. Okay, so I will try to make some more elementary discussion of this one. Another one is there's a geometric picture to see that in terms of the intersection of symmetry defects. So the SO3 symmetry is a zero-form symmetry. As I discussed before, we are in 3 dimension. So this is generated by some surface operator that you could wrap a local operator on it. And you could see that the intersection of these surfaces are some lines. If you intersect 2 surfaces, is a line. And so these surfaces becomes transparent in the infrared because there's no local operator that they could act on. The SO3 acts trivially in the infrared, doesn't act faithfully in the infrared. So the surfaces becomes kind of transparent in the infrared, but the intersection remains non-trivial. And the fact that that is the intersection of these symmetry operators becomes a one-form symmetry in the infrared. And the third way is using Lagrangian. So by performing a large gauge transformation of SO3, you could see that they would act as a one-form symmetry transformation on U1 gauge field. That's another way to see the symmetry transmutation. So now let me just focus on the geometric picture. So for simplicity, let's just consider a Z2 times Z2 subgroup of SO3. So because the matter field transform projectively under SO3, they also transform projectively under the Z2 times Z2 subgroup. So let's say that this Z2 times Z2 subgroup are generated by 2 topological operators, UX and UY. Okay? Then, as I said, there are 2 pictures. One is that the claim is that the intersection of ux and uy is the transmuted Z2 one-form symmetry. The other fact is that the background gauge field for BIR is the cup product of these two background gauge fields. So these are one discrete one-form, so discrete one Z2 gauge fields, and then you could take the cup product to get a two-form discrete gauge field. So let me discuss this intersection point. This is the way to see that. So here, the vertical line is some boson line that transforms projectively under Z2 times Z2. So the fact that it transforms projectively is that the left picture evaluate to -1. Okay, so if you do ux, uy, it differs by minus sign by uy, ux. Ux, uy is minus u1, ux. So the left picture evaluate to -1. Okay, that's just a fact that it's transformed projectively. But now, since these surfaces are topological, the left is equals to the middle, right? You could just wrap these together and find this picture. You know, if you have this intersection, you could make these surfaces flat and you get this picture. So now in this picture, you see that these two surfaces intersect at a line in the middle. And what I discussed before is that these surfaces in the infrared become transparent. The only thing that remains from them is the intersection point, is the intersection line. So we will see that the intersecting lines, when it's wrapped the Wilson line and you shrink it, you should get a -1 because of the left picture. So that's exactly the picture that the Wilson line is charged under this topological line. So this shows that the projective representation leads to the fact that the intersection of these two surface operators generates a one-form symmetry in the infrared. Any question?
Can I ask something?
Yes.
So if you have like a topological surface operator defined not on a closed surface but on an open surface, then on the boundary we have some sort of like improperly quantized line operator. And this
It would
discussion
be
here seems,
non-topological usually.
yeah. So this discussion here seems very related to that. How are they compatible? I cannot see them.
I mean, I don't see why they are incompatible. So you could perhaps also consider if there is an open version of these surface operators, perhaps you could also consider the open version of them. And then the picture would be you have some open version, but you could close it from below or above. And they might differ by some answer, and they might be controlled by some projective representation. It is possible to also derive them from such a picture. I don't see any incompatibility between them.
I mean, I was confused because here you have the line operators to be topological. It is the intersection.
So the red one, yeah.
Yeah, but if you have like an open surface operator, the boundary line operator is not topological in general, right? That's why I was confused. Like it doesn't have to be topological in general, but here it is. Why is it the case? That's what I cannot see.
Oh, it is a case because the whole surface is topological. So if this is the intersection of two surfaces, we could first shrink the surfaces and then consider the intersection.
I see. I see. Okay. So
So
it's not
because
like
the
a
surfaces are
single surface.
topological, their intersection is also topological. Yeah, yeah. This is different from the
Yes.
boundary case. Yeah, yeah.
I see. Okay. Okay. Thanks.
Right. Okay, so now let me pass through this slide very quickly. This slide, I just want to say that using this map between the background gauge field, this theory has an interesting Tooth anomaly, and you could use that to match the Tooth anomaly between UV and IR. So that tells you that these symmetries are exact, and it's an important thing. Okay, so let me not go through this fact. And then, yeah, in the interest of time, let me discuss the second example. Okay, the other example is actually a very familiar example. It's just basically the usual QC, with just the one flavor QCD. So just consider QCD4 in 4 dimension with one quark, the single quark. So this theory has actually a U1 baryon symmetry. Okay, so it's 3 plus 1, the SU3 gauge theory with a quark which transform under the triplets of U3. And so then the global symmetry is U3 mod SU3, which is actually U1. Okay. But the fact is that the gauge invariant operators have integer charges, but the matter field has a charge 1/3. So the quark has a baryon charge 1/3. So it's kind of a projective. It's almost like a projective representation of U1. And so, yeah, this is what I've written here. The quark has a U1 baryon charge 1/3, but gauge invariant operators have integer charges. So this leads to the fact that U1 baryon transmute into a Z3 one-form symmetries at energies below the mass of the quark. And this transmutation is given by this equation. So if you turn on background gauge field for the U1 baryon, such that the Chern class of this U1 baryon number is non-trivial mod 3, then you could construct a non-trivial background gauge field for the infrared pure Yang-Mills theory one-form symmetry. So the infrared is some just pure SU3 gauge theory. It has a one-form symmetry, but this one-form symmetry is not emergent. It actually is transmuted from the U1 baryon symmetry in the UV. So you could turn on background gauge fit for it. In this case, there is no anomaly matching, but at least you could use it as a probe. So even though there are fundamental fields in the UV, there is one. And so now you could also discuss different phases of this QCD.
Can you go back to the previous example?
QED?
So no, this one, QCD4. So are you telling us that if I insert two test charges here in, let's say, in fundamental representation or two index representation, are you telling me that they will not be screened?
So later on, I will discuss different phases, and I will discuss the phases when they are screened or not, and the connection between that. So here I'm just making some kinematical statement that if you go below the mass of the quark, you have this one-form symmetry, and you could get it from here. But of course, in this case, the theory is still, is confining.
So will there be linear confinement between external test charges here?
So this is only valid if you go to an energy which is much, much below the mass of the quark. So I'm imagining, I will discuss it, maybe you could ask later when I discuss the energy regime in the next slide.
Okay.
Yeah, in the slide after that, I will discuss that regime.
Okay, sounds good.
Yeah. So let me first discuss three different phases for this QCD. So let me ask some kind of a Higgs field or scalar fields. One is in the adjoint representation and one in the symmetric representation in 3x3, which is given by 3x3 matrices. Okay, the 6-dimensional representation. So consider the Lagrangian QCD and add kind of a master and Higgs potential. Okay, so the first scenario is a scenario where all these matter fields are very heavy and their masses are much heavier than the QCD scale. Okay, so the quark is heavy and both of them are heavy. So this is believed to be trivially gapped phase in the infrared because you could just integrate everything out and you just left with pure QCD. And another scenario is when both of these are confining. So they would be a completely Higgs phase. Okay, I have it here. So the first one is kind of the confining phase. The second one is a phase that you completely Higgs the SU3 via these two Higgs field. And there is a third scenario that you add this one, but you Higgs SU3 down to its Z3 subgroup. Okay, so there is still a remaining Z3 gauge theory. Okay, and this gives you a deconfined phase. Okay, so the first one is a confined phase. The second one is a Higgs phase, which from the low energy, deep low energy theory, they are kind of indistinguishable. The confined and Higgs phase, they are both featureless. And the third one is the deconfined phase, where the infrared theory is you have still some Z3 gauge theory. So now let me discuss these three phases, which are familiar from the perspective of these symmetries, from their symmetry perspective. So in the second phase, is featureless, is Higgs phase, you have nothing, even no symmetry transmutation. In the third phase, what actually happens is that, as I said, below the mass of the quark, there is symmetry transmutation. And then this Z3 one from symmetry, which is transmuted from U1, is spontaneously broken. So in the first phase, that's related to method question, is that there is some intermediate energy scales, which in that intermediate energy scales, you have transmutation into a one-form symmetry. So if you consider, if you go to mass, which is much higher than the QCD scale, but much below the mass of the quarks, such that you cannot pair create any quarks. In that energy scale, you have some kind of a confining strings, and they're controlled by this Z2 transmitted one from symmetry. But I'm not making no claim about the deep infrared. If you go to deep infrared, it's featureless, you see nothing. Only at this regime of intermediate energy scales, it seems to be there seems to be some Z3 one from symmetry. And it would be very interesting to understand what's actually happening that in intermediate energy scales. Okay. So now one open question is that if this has any implication for this Higgs confining continuity, that at low energy, the Higgs and confining regimes are continuously related. But the question is that is there a distinction between Higgs and confinement at this finite intermediate regime that I mentioned? And the next is some relation between the Higgs SPT. So let me conclude with some summary and outlook. So we discuss symmetry transmutation, and it's important to discuss symmetry transmutation because they could be crucial for matching anomalies between UV and IR. And then there could be also some lattice system. For example, lattice translation symmetry can transmute into high form symmetry in the IR, and this LSM anomaly can match the anomalies. And there is another application in the context of symmetry extension, and this I discuss. And the other question is that if there could be a symmetry transmutation for non-invertible symmetries. Okay, good. Thanks for attention.
Okay, thanks for this great talk.
Yeah, for going over time.
Any questions?
I have one. Hi, Sahand.
Yes,
This is
hi.
what's the example of this lattice translation transmuting into higher form symmetry?
For lattice translation?
Yeah.
Yeah. So there are many examples. One of them was recently discussed by a paper by Nati, Senthil, Mong, and Seth. But so one of the examples actually that started this project was about this one. So we didn't discuss it in the paper. So actually what we found that we haven't written it down is that if you consider Heisenberg model in higher dimension, just Heisenberg lattice model on a cubical lattice. If you consider 3+1 dimension, it seems to be that the lattice translation transmit into a higher form symmetry, to one form symmetry of the model.
I
To have
see.
some second model.
Actually, I wanted to ask about lattice models because all the examples where you were giving were theories, and then
Yeah, so Heisenberg model, so Heisenberg cubic model, in 3+1 dimension.
But even if I break this Z2, let's imagine I only have this Z2x times Z2y symmetry, and the spin 1/2 indeed transforms projectively under that. Even if I break translation, are you saying that maybe I can find a lattice model where there would be some transmuted higher form symmetry?
Okay, so are you looking for lattice model from lattice translation or internal symmetry to higher form?
Actually, both. So I had two questions, and some of it delved into my second question. Yeah, some lattice model with because your Z2x times Z2y symmetry with that's exactly essentially something like Heisenberg square lattice. But let's imagine that I break translation and then I
Okay, so I forgot. So first of all, in our paper, we have I should have maybe answered with that. We have a very, very elementary lattice model, even in 1+1D. So in 1+1D, the one form symmetry is kind of not as interesting as higher dimension, but still we could have a one form symmetry. And we have a very explicit and very easy and solvable lattice model in 1+1D, which you start with this kind of a type 3 anomaly between three Z2s.
Yeah.
And then you go to a phase whether there is two vacua, which is spontaneous symmetry breaking.
Oh,
So,
I see.
and in those cases, so the Z3 cube does not act faithfully in the infrared. Only one
Yeah.
of them act faithfully because we have Z2 spontaneous breaking. And the other Z2 symmetry actually becomes a one-form symmetry. And you could write a formula like that. So you could exactly write a formula such as that.
In
And
that
then
case,
the intersection of two line operators becomes a point operator.
you are thinking of the order parameter as the
Yes,
one.
as a one-form symmetry. Yeah, precisely. Yeah.
Okay, I see. Yeah, thank you. I'm maybe imagining that in higher D, maybe if I start with internal symmetry but still stabilize some sort of topological order, I'm imagining if that would be the analog of what you are saying in 1D, but I'm not very sure. Maybe I should think a bit.
Yeah, should be possible. Should be possible. I mean, certainly there are other examples. I mean, if I
Yeah,
think more, I could come up with example. Yeah, thanks for the question. Thanks for
thanks for the talk.
Yeah.
Any other question? Actually, I have one if no one has. So all of these results, can we understand these from the symmetry TFT perspective? Like,
Ah. So that's a good question. So first of all, I should say that this kind of asymmetry transmutation, it has a kinematical perspective and has a dynamical perspective. So dynamical perspective is whether the symmetry acts faithfully or not. So you have some symmetry, you have to integrate out something else. So the main feature is a dynamical feature, which you cannot capture by symmetry TFT. But yet there is also a kinematical perspective that you might think you'll be able to capture it via sim TFT. And the kinematical feature is kind of this map. This map. So this is the kinematical description of symmetry transmutation, that you get some zero form symmetry and somehow you map it to a higher form symmetry. So this is some kind of a notion of higher homomorphism or some kind of functor between the UV symmetry and IR symmetry, which is also used for anomaly matching. And I should say that actually I don't know how to, even for the case of, zero form symmetry to zero form symmetry or some non-invertible zero form symmetry to zero form symmetry, how to discuss this functor from a UV to IR symmetry in terms of symmetry TFT. So I don't know. Yeah, interesting question.
Yeah, but the perspective, like you had this second perspective where you were intersecting the service operators and the intersection line became topological. So maybe that can be captured by the SimTFT, because when people discuss the SimTFT, they usually use this geometric intuition where the breeding between the two operators in the SimTFT become either the topological operator or the charged object. Maybe if you cook up something, very complicated in the one-dimension higher slab, and you somehow capture this intersection.
Yeah, that should certainly gives a clue, but I don't know what's the answer. Like you have a SimTFT for this guy, you have a SimTFT for the other guy, and there should be some kind of interface between them and some interface between the gapped boundaries. But what property these interfaces have to satisfy, I don't know. But yeah, that geometric picture should give a clue.
I see, yeah. So
Yeah,
there
maybe
should be
this
some interest.
picture would be helpful. Maybe that's what Sahand was trying to go. Like you start with this transfume. I don't know which topological order or which TFT should be the larger one, so to say. But there is this picture about you stack different topological field theories with some maybe partial condensation, and the partial condensation is essentially tells you the emergent symmetry below some energy gap, or the whatever symmetry remains below the gap, and maybe that's that sometimes capture partially the emergent symmetries. Maybe it can also capture this transmuted ones.
Yeah, the issue that I'm having difficulty seeing is the arrow, because so here the arrow goes from one one symmetry to the other. But in SymTFT, if you consider kind of interface between two of them, the interface doesn't see the arrow. So there should be a way to understand it. I just don't see how to see because the interface is kind of symmetric.
I see.
But this is kind of it is very important that the arrow is from one side to the other.
Yeah. I see.
Okay, thanks. Maybe I can stop the recording, and if anyone has questions after record, we can have it.